Okay, perfect. All right. Yeah, so I'm Wouter Schutijzer. I'm working at Umicore at R&D in Ole. It's a small town in east of Antwerp in Belgium, and there I'm part of the recycling and extraction technologies platform. So working on our recycling and refining flow sheets, and I'm a so-called competence manager electrochemistry. So I'm responsible for all development of our electrochemical processes in Umicore. So yeah, here's the content. It's a rather short presentation, but I'll quickly go over it. So first I'll give a very short introduction about Umicore, then a short introduction about electrochemistry, although I don't think that's necessary anymore. Then I'm going to talk about electrometallurgy, chloralkali, and water electrolysis, as these are the main electrochemical processes in industry. So first about Umicore, I don't know if you're familiar with this company, but it's a Belgian company. We're based in Belgium, mainly Belgium, Germany, and Korea, and also have locations all over the world. I will show that in the next slide. But our main activities are catalysis. So we're one of the leading suppliers of automotive catalysts. We're active in battery production of battery materials, cathodes, and also now scaling up our anode production. And we're one of the world leaders in recycling of electronic waste, and also now are ramping up our battery recycling activities. So we have a small battery recycling facility now in Belgium, and the plan is to ramp that up in the coming decade. So yeah, we have about 11,000 colleagues, employees, located all over the world. As you can see, mainly in Europe and Asia. So rather big company, and some numbers. So we have a revenue of about 4 billion. And 300 million spent on R&D, which is a good share of the money spent on R&D. Okay, so then I'll talk about electrochemistry in industry. So for a short introduction, you've probably already seen this, but when we think about electrochemical processes, the first thing we do is we're going to look at the reduction potentials of a process. So an electrochemical process always comprises two half reactions, an anode and a cathode reaction. And just to get an idea about, just to know if it will be a spontaneous reaction or if it's not a non-spontaneous reaction, we're going to look at the reduction potential. So here you see a table of all our reduction potentials. Not going to spend too much time here, but you have two types of reactions. So you have spontaneous reactions and you have non-spontaneous reactions. So on the left-hand side, for instance, it's a school example. If you would have a tin and copper bar immersed in tin and copper solution, if you would electrically connect them, then you would have a spontaneous reaction in which tin is oxidized and copper is reduced, and that is because the reduction potential of copper is larger than that of tin. If you would apply a current voltage, then you could actually reduce tin and oxidize copper. So the right-hand side, that's what we call electrolytical processes. And actually all processes I'm going to talk about are non-spontaneous electrolytical processes. So we use electricity to mainly to deposit metals from a solution or from other media, and at the same time there's an anodic reaction taking place. Usually this is water oxidation, in which you form oxygen. But we also a few other examples. So industrial electrochemical processes, for us, this is mainly metal production, so production of copper, nickel, alumina, for instance. Then you also have electrolyzers, hydrogen production from water splitting, fuel cells, chloralkali industry, in which you produce chlorine gas, sodium hydroxide. The most well-known application of electrochemistry in daily life is batteries, the lithium-ion batteries, for instance, and that will not be covered in this presentation, although this is an important activity of our company. But I'm sure you are aware of how that works. So now we're going to go to electrometallurgy. So what we do in electrometallurgy is we use electricity to try to recover metals, to reduce metals, for instance, and also sometimes to leach metals, to electroleach metals. And this needs to be done in a certain media. So of course the preferred media is water, aqueous media. But the problem with water is that that it's not stable at all potentials. So if you want to work with water, you need to make sure that you work in the stability region of water. So for instance, you need to see if the reduction potential of the metal you want to recover, for instance, is in the stability region of water. If it's not, then you need to look to other media to work in. So if you look at the table, for instance, so here you can see in a lot of metals indicated which fall in the stability region of water. So quickly take my pointer if that is possible. So you can see here you have the oxidation of water to oxygen on the one hand side, and then here you have the reduction of water to hydrogen. So you want to actually work in between those potentials. If it's close to that, that's also still fine to work in aqueous electrolytes. But for instance, if you're looking at these type of metals like alumina, magnesium, sodium, you cannot produce these metals in water media, because then you will just convert your water instead of reducing your metal. So then you need to look to other media such as fused salts. But all the other metals indicated here you can process in aqueous media. And so this is mainly about the reduction of metals. The counter reaction at the anode is usually, as I said, oxidation of water to oxygen. So that's what usually happens at the anodes. Then first I'm going to talk about molten salt electrolysis. So these are the metals with a very low reduction potential. So these are processed in molten salt media, for instance, alumina, sodium, magnesium. You can see here this is done at very high temperatures. So let's say between 500 and 1000 degrees Celsius. This doesn't look too familiar probably, but just want to show that the current densities that we're working at are very high. You don't have a comparison right now, but you'll see if I compare it to, for instance, electrowinning, that the current densities are very high. So let's say definitely above 1000 amps per square meter. Just to give you some examples, so this is, for instance, the Halt-Héroult process, which is used to produce alumina. So this is an electrolysis reactor using the fused salt. And what you have here is you produce molten aluminum at the cathode, and the anode, the counter reaction at the anode is actually oxidation of carbon anodes to CO2. So that's the counter reaction that happens. So you can see here the total reaction equation. So that is alumina production. So all alumina in the world is produced in this way. Very energy intensive process. So show you here you have the energy indicating the energy consumption. So it's quite energy intensive, above 10 kilowatt hours per kilogram. Then, for instance, we also have magnesium production, which is also done in molten salt media. Here you have this counter reaction chloride formation. There's also a special cell design, which this is done. Then we go to electrowinning. So this is what we are actually doing in Umicore. We are also performing electrowinning. So in electrowinning, you do it in aqueous media, usually in an acidic solution. You can see here, usually in a sulfuric acid solution. You have a cathode on which you deposit a metal such as copper. At the anode, you have oxygen. You oxidize water to oxygen. As you can see here, the temperatures are much lower. What you also see is the current densities are much lower than the ones indicated for molten salt electrolysis. So this is the downside from electrowinning in aqueous media, that the current densities are much lower. As something I didn't mention, the as you use electrons to reduce a metal, the metal production is directly correlated to the current density. So what you want is you want to maximize the production capacity of your installation. So you want to maximize the current density at which you work. And for electrowinning, you're limited to do that. In aqueous media, for the molten salt electrodes, you can go to very high current densities. But plus side is, you can see here, the energy requirements are much lower compared to molten salt electrodes. Also, of course, has to do just thermodynamically with the reduction potential of the metals. That these metals have a lower reduction, have a higher reduction potential as the other, as alumina, as sodium, as magnesium. But it's also because of the process that the energy requirement is much lower. Just to give you an idea about energy consumption. So before we talked about the thermodynamic potential difference. So in the table with reduction potentials we showed, you have the anodic reduction potential, the cathodic reduction potential, and the difference between the two gives the thermodynamic potential difference. So for instance, for copper electrowinning, you have 1.23 volts anodic potential, 0.234 volts for copper for copper reduction. The difference between those two is about 0.9 volts. So you say, like, in the very like the most optimal conditions, you could operate the process at 0.9 volts, but in reality you operate the process at about 2 volts, and that's because you have a lot of other additional potential additions, and these have to do with resistances of the system. So you have at the cathode, at the anode, you have overpotentials. You have a resistance of the solution. You have other resistances, and these all accumulate into the cell voltage. So unfortunately, you cannot work at the thermodynamic potential, or the theoretical potential, and then you arrive at this energy consumption, specific energy consumption for copper electrowinning. To give you an idea how this production facility looks like, here you can see a typical copper electrowinning plant. So we call this a tank house. So it's filled with electrowinning cells. So these cells are just big bots filled with electrolyte, and then you have all these electrodes in here. So these you have cathode, anode. So right next to each other, sitting in these cells. These are filled with electrolytes. Electrolyte flows through it, and then copper is deposited on the cathodes. Here you can see how these cathodes look like. So you have, we call it the blank. It's a stainless steel plate, and there on top of it there's a copper layer deposited. So it's a copper plate deposited on the blank. These can be removed from the blank. It's done by what we call a stripping machine. So they flex the cathode, and then the copper plates, they fall off, and then they're packed, as you can see here, and then the blanks, after they're stripped, they're just put back into the cell, and you start the process again. So this usually takes about 7 days to create to produce a copper plate in this way. Yeah, so to give you an idea about how this is incorporated in a typical process, so we usually talk about flow sheets. So we have a flow sheet to process a certain material to get the clean metals, to get the clean metals out. And this is a well-known flow sheet which is used in Nikkelverk in Norway by a company called Glencore, and they use besides copper electrowinning also nickel and cobalt electrowinning. It's a complex flow sheet, but anyway, they are able to have the feeds that contains all three metals, and they're able to separate the metals and separately separately perform the electrowinning process and produce copper cathodes, nickel cathodes, and cobalt cathodes, and they are able to separate these metals by precipitation of metal or by solvent extraction. So solvent extraction, for instance, is also applied at a lot in the metallurgical industry. This is what a nickel tank house looks like. Nickel plates, very similar to what I showed for the copper plates. Then another process we have and this is actually much more applied even in electrorefining. We don't do it in Umicore, but it's we used to do it. It's it's electrorefining. So what you do in electrorefining is you have the combination so you of electro leaching and electro deposition. So where we had as anode reaction before in electrowinning oxygen formation, here we actually have the anodic reaction, the oxidation of the metal and the dissolution of the metal in the electrolytes. And the cathode reaction is the same. We deposit the clean metal. And this is actually a way to purify a metal, because you can, in this way, you can have an impure cathode with a lot of impurities in it, and you can deposit a very pure metal. So for instance, most copper is processed in this way. And another big advantage of this process is that as you can see here, the cell voltage is very low. And the reason for this is that the theoretical cell voltage, if you look at the reduction potentials, is 0, because the oxidation and reduction reaction are the same. So it's actually a very energy efficient process. Downside of the process is it's slow process, but it's a very efficient process. And there's a lot of metals you can process in this way, like besides copper, also nickel, cobalt, lead, tin, but it's mainly applied for copper. So if you look, for instance, next slide, here we have also a tank house with the electrifying tank house. 80% of copper is produced, about 80% of copper is produced in this way. These numbers are not completely correct anymore, but 80% is produced in this way, about 20% is produced by electrowinning. This has to do with the feedstock, the form in which copper is present in the feedstock if you choose one or the other process. As I said, it's a way to actually extract the metal from an impure material. So here you have an impure anode. There are a lot of impurities present in the anode, and you can selectively extract the metal and deposit it on the cathode. So this is a way to purify your metal. This is applied a lot. And this, you get a very pure copper. The impurities, they all have different behavior. Some will not dissolve, others will dissolve and precipitate, other will stay in solution. But it's only copper that will deposit on the cathodes. So this was a short intro to electrometallurgy. Now we'll shortly talk about chloralkali. We don't apply chloralkali, but it's an important process in industry. So we'll shortly talk about it. Chloralkali, what is it? It's actually the conversion of sodium chloride into sodium hydroxide and chlorine gas. The chlorine gas is used to synthesize chlorinated organic compounds, such as to produce PVC or isocyanates. The sodium hydroxide has a lot of different applications too, and it's applied a lot, this process. There are there were three technologies to do it, called a mercury cell, diaphragm cell, and a membrane cell. But here on the bottom, I've shown the application of these technologies in time, and as you can see, at the moment, it's almost only the membrane cell technology that is applied. So what happens here in this process? You have an anode side, a cathode side. At the anode side, you feed it with saturated brine, sodium chloride solution. You produce chlorine gas at the anodes, sodium migrates to the cathodes, you produce hydrogen gas at the cathode together with OH minus, and you produce sodium hydroxide at the cathode. So very similar to the process that Guillaume just shown for lithium. There's here's a bit the advantages, disadvantages of each technology, but anyway, this technology is by far the best technology. It produces a very pure solutions, the lowest energy consumption. The difficulty of such a process is that you need a very, very pure brine. There cannot be any impurities present in the brine because they will contaminate the membrane, or they will have an influence on the electrodes. But by far the best process, the membrane cell technology. So just to show you, this is the typical production facility as it look like. So here you can see the big cell stacks, what it's called. So these cells, in these cells, um, electrodes and membranes are all in series. So you have all cells which are stacked next to each other. So we call it a bipolar design in which they're all stacked in series, these cells. Here you can see the required purification that is needed. So you have it's a lot of purification of the brine needed before it can be fed to the cells, and then afterwards is also after treatment you need to concentrate the solutions. So it's a complex process, but it's a very effective process. Here are some process conditions, not that important, but as you can see, the current density, again, we always like to compare it, very high current densities. So let's say at least like about 10 times higher than the ones that we see typically in electrowinning. And as I said, current density is a measure for the production rate and also for the size of the facility you need. Because if you have higher current density, a higher production rate, and you can go to a much smaller production facility. Then, as last, I just want to talk about electrolytic hydrogen production. It's also something that we are not involved in. We are involved in it in some ways, but we don't perform this process ourselves. So I'm sure you all have heard about hydrogen production. So also electrolytic process in which you split water and you produce hydrogen at the cathodes, oxygen at the anodes, and you have a lot of different applications for hydrogen. You can use it as a fuel. You can convert it to synthetic fuels. You can convert it to other chemicals such as ammonia or so. You can use it to heat your house. A lot of opinions about hydrogen, if it's useful or not, but what's certain is that there will be a large application of hydrogen in the future, just because we need it a lot in industry. So there will be a lot of hopefully there will be a lot of renewable hydrogen produced in the future. To produce hydrogen, there are four main technologies. It's shown here. Not go into detail, but so we have a solid oxide electrolysis cell, which is a high temperature process, and then we have like the lower temperature processes, which all are electrolytic processes involving electrodes and membranes. So we have, for instance, alkaline electrolysis, which uses concentrated potassium hydroxide solution. We have a PEM electrolysis, which involves a proton exchange membranes and very expensive electrodes, as they require PGMs. We have a rather new development, which is called anion exchange membrane electrolysis. So it's like a mix of those two. It combines the advantages of both of these. Let's say because it also has like it has an anion exchange membrane which can be used, and it has the advantages of a PEM electrolyzer, that it has high flexibility, low footprint, and it has the big advantage of alkaline water electrolysis, that it has a low system cost, because the alkaline electrolysis disadvantage of it is that it's not very flexible. It has a limiting operating pressure. You want to produce gas at pressure, and also you work with a corrosive electrolyte, namely potassium hydroxide. In these technologies, you can work with water or with like dilute electrolytes such as potassium hydroxide, but here you use very expensive electrodes. Here you can see a distribution of the technologies, how they are applied. And as you can see, it's actually the alkaline water electrolysis is and will remain the main technology for the future. Then you have PEM and alkaline electrolysis membrane electrolysis will play some parts. Hopefully it will grow, but this will remain the main application, because it's a very robust, mature technology. It works very well. It's very stable. just show you some pictures. This is how a typical alkaline water electrolysis facility looks like. So you have a cell stack in which the same as with the chloralkali, in which you have all the cells stacked together in series. They're pushed together. Here is a this is show it more in detail how it's made. So you have membrane. It's not a membrane. It's a diaphragm that's used. You have electrodes. You have some other components, and they're pushed together all in series. And you put you let current flow through it, and then you get the gas formation, which is collected at the top of the cell. Here you have a typical PEM electrolysis stack, looks like, and here's shown a bit more in detail. So these are now these applications are really growing now, and the stacks are becoming larger and larger. And also here, goals always to try to push the current density, because yeah, it's directly correlated to the gas production rate. So there's a lot of developments in this technology to try to increase the performance and the production rate. So this is a short overview of the main electrolytic applications in industry. I hope you enjoyed it a bit. Definitely let me know if you have any questions about it. So we are we're investigating all new applications of electrochemistry for metallurgical processes, but there are also a lot of other applications for it, which is very interesting. So thanks for your attention, and let me know if you have any questions.